Hello, everybody. Welcome to today's lecture. So today we're going to start talking about confidence intervals. So this is the um, inferential statistics part of the class that I've been talking about. So chapter 2 is the descriptive statistics. So those are the statistics that we would look at, and we just use it to merely describe the data. So like, what's the mean? What's the standard deviation? What's the proportions? That kind of stuff. We weren't really making any conclusions. Now with inferential statistics, we're going to be able to use our samples to make predictions about the populations. Okay. So, let's write down like a quick definition of the inferential statistics then. Just in my own words here. Inferential statistics is the part of statistics concerning estimating population parameters using sample statistics. Okay. So oftentimes we want, to know something about a population, but we realistically can only work with samples, right? So if we wanted to know, like us personally, if we wanted to know who was going to win the presidential election, for example, our best bet would be to take a sample of people, a random sample, and ask them who they're going to vote for. Then we would use that data to make a prediction about what's going to happen in the entire country, right? Because we couldn't ask every single person, so we would just use a sample. So when we do that, there's inherently going to be some kind of error, right? It's not going to be absolutely perfect because when we take that sample, we could miss like a key part of the population, so we don't account for them. So we're only going to be sure with some to some degree of probability, or what we're going to see in this section, we're going to have some level of confidence. Okay. So that leads into what we're going to talk about today, which is confidence intervals. So let's first define something called a point estimate, which is really not much to even say here. I'm getting all this from the introduction to chapter 8, by the way, not exactly 8.1 yet. So let's let x bar be the sample mean. So this is the standard notation that we introduced back in like chapter 2. And S be the sample standard deviation. Okay. And then of course we're going to let mu be the population mean, just like normal. And sigma be the population standard deviation. Okay. So all the same notation we used back in chapter 2. We have x bar for the sample mean, mu for the population mean, S for the sample standard deviation, sigma for the population standard deviation. Okay. then we say X bar is the point estimate of mu. Okay. So, and then this S also, whoops, I'll stay with that pen. Also, S is the point estimate of sigma. Okay. So in other words, we just take whatever the sample mean or the sample standard deviation or sample whatever is, and we say that's the point estimate of the population mean. So we basically just don't do anything else to it. We just say, okay, well, if the sample mean is this, the population mean is probably also about this, right? So let's say, for example, that I have like 4 sections of Math 101, okay? So let's say that there's 100 students between all 4 sections. And in one of the sections, I have 25 students, right? Or let's say all 4 of them have 25 students. Then what I would do is I would take just one of the classes. I would take their average grade. Let's say it's a 75%. And then I would say, okay, since this section has a 75%, I'm going to estimate that between all of the sections, the average test or the average grade is a 75%. Okay. So I just don't do anything extra to it. I just take whatever the sample mean is, which in that case would be the 75%, and say, okay, that's probably about what the population mean is. Okay. Now, of course, this isn't necessarily going to be super accurate, right? It's kind of risky to use this because maybe the people in that section are performing wildly different than, say, the people in another section, right? There's a lot of factors at play there. So I wouldn't want to do that, right? I would want to try to make the sample, I would want to try to make the estimate a little more accurate. And that's where confidence intervals come into play. For confidence intervals, we're going to take the point estimate, and then we're also going to incorporate a margin of error into it, okay? And by the way, X bar, S are called statistics. Just as a reminder, it just kind of throws that in there. That's something we talked about back in chapter 2. Okay. Any numbers coming from the sample are statistics, and any numbers coming from the population are parameters. Okay. So now a confidence interval is a different type of estimate. In which we have a range of numbers instead of just one number. Okay. So we use a range of numbers instead of just one number. This should hopefully make sense, because if we take our sample mean and say, okay, the population mean is probably this, well, there's going to be a very low chance that that's true, right? If my one class has an average of 75%, it's very unlikely that all 4 sections have a average of exactly 75%. So instead, we want to look at a range of numbers and say, okay, based on the fact that one section has 75%, all four sections, they probably have a percentage that lies between this number and this number. Okay. So it opens it up a lot more so that the chance that we are correct in our prediction is way more likely. Okay. So a confidence interval provides a range. So this is like the real definition here. A confidence interval provides a range of reasonable values in which we expect the population parameter to fall. Okay. So it gives a range of values in which we expect the population parameter to fall. Now, it's not going to be guaranteed to fall in this range, of course, but the advantage here is that there will be a predictable level of confidence that the numbers will fall into this range. Okay. We'll be able to say, for example, if we construct a 95% confidence interval, that we are 95% confident that the numbers fall within this range. Now, there's a little bit of nuance here in that we won't be able to say there's a 95% chance that the numbers fall in this range. And that's a very common trap with these. We're not really going to dive into the nuance of, it's really semantics at that point. But the idea is we look at the population parameter as a fixed number. It's not random. So it's either in the interval or it's not. There's no randomness to it. So we don't say that there's a 95% probability that it falls in this range. Instead, the interval itself is what is random. The book mentions that the confidence interval is technically a random variable. So when we say that we're 95% confident or however confident that the number falls in this range, that is a statement about the test we're conducting, not about the probability of the parameter. Okay, because there is no probability with the parameter because it's a fixed number, right? If we are trying to guess who's going to win the presidential election, the number of votes a candidate is going to get is a fixed number. It's not random, right? Maybe it's not fixed right now, but at the time of the election, it will be fixed. So the 95% confidence is about our test, not about the parameter itself. That's all I really want to say about the nuance. It's kind of a deep subject to really get into. I just really want you to be aware that that is what we're going to be constructing here. Okay. So as I said, we're going to be able to construct what's called a 95% confidence interval, a 99% confidence interval, etc. The most common one being the 95% confidence interval, because 95, it's a big number, right? If we're 95% confident that the number is in this range, that's pretty good. That means there's only a 5% level of confidence that it's not. So we've actually already seen this before. If we look back at the empirical rule, right, we saw that 95% of the data falls within 2 standard deviations. So when we constructed where was it? This part right here. We got 0.95, right? So The 6 to 18 here, in this example, and just as a reminder, for this example, the mean was 12 and the standard deviation was 3. So 6 to 18 is a 95% confidence interval. Okay. Because we're 95% confident that the number is going to fall within this range. Okay. And this is exactly how the statement would be read too, that the probability that our random variable x is between this number and this number is equal to 0.95. Okay. So let's the book uses an example here. Let's say let's say x bar is equal to 2 and s is equal to 0.2. Okay. Sorry, s is equal to 0.1 in the example. And the sample is normally distributed. Okay. Then by the empirical rule, okay, so just like that example I just showed, 2 minus 2 times 0.1 up to 2 plus 2 times 0.1. So what am I doing here? This is the mean. This is the standard deviation. So I'm going 2 standard deviations to the left, 2 standard deviations to the right. Okay, that's what this interval is. So 2 times 0.1 is 0.2. 2 minus that is 1.8. And on the other side, we have 2.2. This is a 95%. I'm just going to write CI, confidence interval. Okay. So with the empirical rule, we don't really have to do any more work, right? When it's normally distributed, if we know the standard deviation and the population or the sample mean, then we can just go ahead and find this number, right? So, a lot of times it's not going to be this easy though, because we can only use the empirical rule on things that are normally distributed, which not everything necessarily is. And what if we don't want to find the 95% confidence interval? What if we want to find a 99% confidence interval, right? If you look back at our empirical rule, we don't have a number for 99%. We have one for 99.7%, but specifically for 99%, we don't have. So we want something a little bit more general. So in general, confidence intervals have the form point estimate minus margin of error, comma, point estimate plus margin of error. So we're taking the point estimate and we're subtracting the margin of error, adding the margin of error. Okay. So our point estimate, we were using X bar here, right? Because we said earlier X bar would be the point estimate. Because the sample mean is a point estimate of the population mean. And I didn't really specify, this is a confidence interval for the population mean. Okay, so that's important to specify. So in this example, we were estimating the population mean using the sample mean. Since the sample mean is 2, we're saying we're 95% confident that the population mean is within this range. So we're using X bar as the point estimate. We were using the standard deviation as the margin of error. Why were we doing that? Well, if you think back, I kind of just mentioned it very briefly. Well, let me see if I can find it here. Right here. Sorry, I need to like zoom out. There we go. So see right here, we said that the standard deviation is called the standard error of the mean. Okay. So it's justified here. Okay, so the population standard deviation gives the standard error of the mean. Now I think that makes me think, yeah, I did accidentally call this S. This should have been sigma. Which may not seem like a big deal, but it is a big deal. Sigma is the population standard deviation. So in this example, we knew the population standard deviation and we knew the sample mean. Okay. We wouldn't have been able to do this same thing with just the sample standard deviation. Okay. So specifically, the population standard deviation is the standard error for the mean. Okay. Now, a lot of times when you see like surveys, like if you're watching the news and they're giving surveys, like, just take into account the presidential election, you might see some survey that says Biden is predicted to get this percent of the vote. Trump is predicted to get this percent of the vote. At the bottom, you'll see a little note that says plus or minus, I would say margin of error plus or minus 2% or something like that. So let's say that Biden is predicted to get it's not usually that high. It's usually something like 48%, right? Because there's more than 2 candidates, so it's not usually above 50. Let's say that Biden's predicted to get 48% and there's a margin of error of plus or minus 2%. Then what they're really trying to say is that they're confident that Biden will get a vote in a range of 46 to 50%, right? They don't usually put the confidence level on there, so it's unclear whether they're 95% confident or 99% confident or whatever. But this is usually what you would see. So you really want to take that margin of error into account. Okay. Let's go on to actual 8.1 now. That was all just from the introduction. A lot of times with books, we tend to like skip the introduction and go right to 8.1, but this one really has some important stuff in all of the introductions. especially now that we're getting into this part. Okay. So 8.1 is talking about a single population mean using the normal distribution. Okay. And it starts up with the section called calculating the confidence interval. And I already did it once, but from this point on, I'll probably abbreviate confidence interval as CI because we're going to be writing a lot. Sorry. Okay. So if we want to construct a CI for a single unknown population mean, okay, mu. So we're specifically looking at, okay, if we're looking for the population mean, that's the only case this is going to apply to. Where we know the population, I'm just going to start abbreviating that as POP, standard deviation, which will say sigma. So we want to be very clear here that mu is unknown, but sigma is known. So we do not know the population mean, but we do know the population standard deviation. That's very important here. Because as we saw, the population standard deviation, when things are normally distributed, is the standard error. Okay. We need one x bar, a point estimate for the mean. Okay. And two, a margin of error we often call to the margin of error the error bound for a population mean. Okay, or EBM. Okay. So in other words, the confidence interval is going to be x bar minus the EBM, x bar plus the EBM. Okay. So x bar minus the error, x bar plus the error. Now, the margin of error, it's going to be different depending on the confidence level. In the last example, we were doing a 95% confidence level. So now we're going to look at some different ones. So at this point, the book starts talking a little bit about that nuance I was talking about, that we're not necessarily saying, like with a 95% confidence level, that there's a 95% chance that the value falls into place here. Instead, we're really saying that the percent of confidence levels that we come up with that contain the parameter value is 95% of them. Again, this is really just reflecting that the interval itself is random, a random variable, whereas the population parameter is fixed. I said I wasn't going to say too much more about that though, so I'll leave it at that. But at the beginning of 8.1, there's a paragraph in the book dedicated to talking about this a little bit. Okay. So, I said we often pick 95% or 99%, but we could really pick whatever we want. And it's really up to us doing the experiment to decide what level of confidence we want for this experiment. Maybe like 51% is good enough, right? I mean, it really shouldn't be, but maybe it is. 95 is a good choice because it is very confident, but it's not so strict, right? There's a little bit of error still, but it's still unlikely to fall outside that range. 99% is a lot more strict. So let's look at, well, let's first introduce a new variable. So I guess I'll just call this notation. We will use the Greek letter alpha to represent the probability that the interval does not contain the population parameter. Okay. And note that alpha plus the confidence level is equal to 1. In other words, the confidence level is going to be 1 minus alpha. Okay. So we can introduce this new letter alpha, and if we want a 95% confidence level, then alpha is going to be 0.05. Okay. Let's say we want to look at a 90% confidence level. Okay. All right, actually, first let's look at this section that talks about calculating the confidence interval first, so we can look at the steps clearly, and then we'll come back to the 90%. We'll encounter the 90% on this path. Okay, so we're gonna go through these steps in order and talk about them as they come up. Okay, so calculating the confidence interval. So first of all, we want to calculate the sample mean x bar. Okay. Remember, we are assuming we are given sigma. Okay. So we would just calculate the sample mean. So, so you would have your data sample, and you would just add them all up, divide by however many there are, that would give you your X bar. And then you'd have to be given sigma. Okay, so we wouldn't need to be calculating that. 2, this is a new one. We need to find the z-score that corresponds to the confidence level. Okay. So what does this mean? Whoops. Okay. Let's remember what the z-score is, first of all. The z-score for a data value tells you how many standard deviations the value is to the right of the mean or to the left of the mean. So if we think back to the empirical rule, one standard deviation to the right of the mean and to the left of the mean is that encompasses the 68%. So if we were thinking about this in terms of confidence intervals, we would say a 68% confidence interval would be the range from one standard deviation, right, to the left and to the right of the mean. So in terms of z-scores, this would mean that the z-score for that would be 1, because the z-score tells you how many standard deviations you are to the right and left of the mean. So for the 68% confidence level, the z-score would be 1. For the 95% confidence level, the z-score would be 2. Okay. We're going to write it a little bit differently from how we normally would here. So let me here. So remember, the confidence level is the area in the middle of the standard normal distribution. Okay. In other words, that 95% confidence level is this area, that purple line, right? So that means if there's 95% of the area in here, then that means in the tails, this part and this part, there are there's 2.5% on either side there. The confidence level is equal to 1 minus alpha, right? That's what we said right here. And that area, so that's the area that's left over, and it's split into 2 equal parts on the left and the right side, right? So each tail contains alpha over 2%, right? So like on the 95% interval, there's 5% left over. So each side contains 5 divided by 2%, or 2.5%. Okay. So the z-score that has an area to the right of alpha over 2, meaning that has an area in the right. If you go to the z-score, then to the right of it, the part that we're not worried about, the part that's left over, has an area of alpha over 2. So in the 95% confidence interval case, here is our z-score right here. So the area to the right of it has 2.5%. We denote that area by z and then subscript alpha over 2. Okay. So for example, if the confidence level equals 95%, right, which is 0.95, alpha equals 0.05, so alpha over 2 equals 0.025, okay, which is 2.5%. So we write z 0.025, okay. So we write z 0.025. So with this notation, that means the area to the right of z 0.025 is 2.5%, right? And then the area to the left of it would be the 97.5%, okay? Okay. All right. Okay, so I got the standard normal table pulled up here. We had a z-score of we're finding z 0.025. So we want to find the value that gives us an area of 2.5% to the right. So we have to be careful about what table we're using. And also notice we're kind of doing it backwards now. So we're going to know the value in the middle and we're going to look for the corresponding z-score. Okay, so let's go ahead and use, well, if you want to do it directly, you could use the complementary cumulative table because this one gives you the value to the right. We know the value to the right is 0.025, so we could just look on this table for the corresponding z-score. And if we do that, we find that it's 1.96, okay? So z 0.025 is equal to 1.96, okay? The way we were doing it last time, we were always kind of converting it to looking at the area to the left. If there's 2.5% to the right, that means there's 97.5% to the left. So we would go over here and look for 0.975. So we just look for that on the table and we find it right here, which again is at 1.96. Okay. Now this might be a little bit surprising because we're doing the 95% confidence interval, which we said was 2 standard deviations. And what we're seeing here is it's not exactly 2 standard deviations. We're basically rounding with the empirical rule. So now we're finding the precise value for 2 standard, well, not 2 standard deviations. We're finding the precise value for the 95% part. And we're seeing that it's actually 1.96 standard deviations. Okay. So step 1 was calculate the sample mean. Step 2 is find the z-score that corresponds to the confidence level. Let's do one more example because I know we kept taking breaks to go look at other definitions and stuff. So let me do one more like full-fledged example here. Okay. Let's say, so this is going to depend on the confidence level. Let's say we have a confidence level of 90%. Okay. 0.90. So then we want to figure out what z is. So to find that, first we need to find alpha, right? So if the confidence level is 0.9, then alpha is 1 minus 0.9, which is 0.1. Okay. I got this because I'm just taking this equation and kind of reversing it for alpha. Okay. You would add alpha, or actually it'd be better just to go back to the original equation we had, which was where? I think I passed it. Right here, alpha plus confidence level equals 1. Just subtract the confidence level from both sides. Okay. Then we get alpha equals 1 minus the confidence level. So alpha is 1 minus 0.9, so alpha is 0.1. So we want z of alpha over 2, which is 0.1 divided by 2, which is going to be 0.05. Okay. So we want z of 0.05. So that's the area to the right of z. The area to the left of z would be 0.95, right? It would be the other part. So you can use either table. You can use the table that we were using, always gives it to the left. So we can look for 0.95 here. So we just have to go through the values until you find 0.95, which is not perfect, but it looks like this is the closest one. So we're at 1.65. You can go on this table instead, and then you'd be looking for 0.05. So we're down here. Where are we? Somewhere around here. This is the closest one, so it's at 1.64. Okay. So you're either using 1.64 or 1.65, depending on the table you're using. 64 is actually, it looks like a little bit closer. This is a tiny bit closer than this one is. So let's go with 1.64. Okay. So there, now we have the z-score. Okay. So we haven't actually talked about what to do with this yet. We need to go down the list to the next step now. See how we're doing on time here. 48. Okay. So after I go through the steps, we'll probably be done for the day. So we're not going to finish this chapter yet. Step 3. Oops, Step 3. We want to calculate the EBM, which is like the error, right? So how do we do that? Well, we do have a formula for it, okay, which we haven't given yet, but here is the formula. EBM is equal to z alpha over 2, so that would be like the 1.64 in this case, times the standard deviation divided by the square root of the sample size. This was a number we saw pop up back in chapter 7. Okay. So now this is dependent on the sample size too. So we also need to know the sample size, which if you did step 1 where you calculated the sample mean, surely you would know what the sample size is, right? It would just be the amount of data that you had. So let's just say, for example, okay, sigma is 10, n is let's say 1,000. Okay. And let's say we were using these numbers right here. Okay. So that we already have the z-score. Then our EBM would equal z 0.05, which we already calculated, times 10 over the square root of 1,000. So that was z 0.05 was 1.64 times 10 over the square root of 1,000. Just do that in a calculator here. Square root of 1,000 is about 31. Yeah, let me just do it all in one step. 10 divided by square root of 1,000 is 0.3162 approximately, because we're rounding here. And then we're going to times that by 1.64, and we're going to get about 0.5186. Okay. So obviously that's a huge error, but that's okay. Okay, so this is the formula we're using to calculate the error. Finally, once we have all that, we can calculate the confidence interval. Okay. So for this example here, well, let's say first of all, x bar is equal to 5. Okay. Then using the information we just found, well, we found that the 90%, I mean, it doesn't matter that it's 90%. We found that any confidence interval has the form x bar minus EBM, x bar plus EBM, and we have all these numbers now. So the 90% CI is 5 minus 0.5186 5 plus 0.5186, which is going to be what? Let's see. Oops. 5 minus 0.5186 is 4.4814, and 5 plus that would just be 5.5186. Okay, so this would be the 90% confidence interval, just given all these numbers here. Okay. All right, let's go through another example. Let me see. Let me find one example that they have here. Here's a good example. Suppose average pizza delivery times are normally distributed within unknown population mean and a population standard deviation of 6 minutes. Okay. A random sample of 28 restaurants, pizza delivery restaurants, is taken and has a delivery time of 36 minutes. Sorry, a sample mean delivery time. Let me just rewrite that. Has a sample mean delivery time of 36 minutes. Okay. Find a 90% CI estimate for the population mean delivery time. Okay. So now we can see one full example instead of having to break it up into pieces like we were last time, which I know could have been a little bit confusing. Let's first identify all the parts we have. So a random sample of 28 restaurants is taken and has a sample mean delivery time of 36 minutes. So our sample mean, our X bar, let's write answer here. Our X bar is 36. Okay. We're given that. Our sigma, we are given to be 6, right? That was the population standard deviation. And our n is 28, right? Because that's our sample size. So this is pretty much everything we're given. And the confidence, we know that we want a confidence level of 90%. That's given in the question. So this is everything we're given. So let's think back to the steps. 1, calculate the sample mean. Already did that. That was given to us in the problem. 2, calculate the z-score. Okay. So what z-score are we looking for? Well, the 90% confidence interval implies alpha is 1 minus 0.9, which is 0.1. Okay, it's basically the leftover part, so the 10%. So we're looking for z 0.1 divided by 2. Okay, 0.1 divided by 2 is 0.05, so we're looking for z 0.05. Now, the nice thing about this is that the z is not changing, right? Because z is standardized. So it doesn't actually matter like all of these numbers. We can just use the z we already found in the previous problem, right? We already found z 0.05 to be 1.64. It's not actually changing. So we don't need to do it again. Okay. So we don't have to recalculate that. So that was step 2, is find the z-score. Step 3 is find the EBM. Okay, the EBM is going to be z 0.05 times sigma over root n, which in our case is going to be 1.64 times sigma was 6 and the n was 28. Okay, so this is what we got. So we'll just throw this in the calculator. 1.64 times 6 divided by the square root of 28. Whoops. Gives us 1.8596. Okay, I mean, you can round to however many decimals you want. It doesn't really matter. Let's make that a little smaller. Let's just say 1.86. Okay. All right. So now that we have the EBM, now we can find the confidence level, the confidence interval. 90% confidence interval is X bar minus the EBM. So 36 minus 1.86 to 36 plus 1.86. Okay. Which is going to be 36 minus 1.86 is 34.14. 36 plus 1.86 is 37.86. Okay. So we're 90% confident that the average pizza delivery time is between 34.14 minutes and 37.86 minutes. Okay. Let's do one more thing. Let's say, what about a 99% confidence interval? Okay. How is this going to change the numbers? Okay. So what's going to change based on the confidence interval being different? Well, the alpha is going to be different, right? The alpha is going to be 1 minus 0.99, which is 0.01. So that means our z-score is going to be different. 0.01 divided by 2 is 0.005, right? So we're now looking for z.005. Okay, so we can go to our table. The complementary cumulative table, that's the one that gives it to the right. So you can look for 0.005 on this one. Let's see. 0.00508, 0.00494. 494 is a little closer. So that's 2.58. Okay. If you wanted to use the other table, if there's 0.5% to the right, then there's 99.5% to the left. So you'd be looking for 0.995 on this table, which we're going to find right. No, that's not right. 0.995. We'd be right here. Right, so 2.58, which is what we had. Okay. Once we have that, we can calculate the new EBM because the EBM changes based on the z-score. So it'd be 2.58 times the 6 over root 28. Okay. So that's going to be, just throwing in the calculator, 2.58 times 6 divided by root 28. It's going to be 2.93 approximately. So now we have the EBM. So the 99% confidence interval is 36 minus 2.93, 36 plus 2.93. Because remember, 36 is the population mean. The sample mean. So this is 33.07, 38.93. Okay. This is the 99% confidence interval. So how does it compare to the 90% confidence interval? Well, the 90% has a smaller range, right? So essentially what we did is we broadened the range a little bit, and now we can say, okay, we're this confident it's in this range. So that's the trade-off. If we increase the confidence, we also increase the range, so we know less precisely what the value is going to be, right? Whereas we can pinpoint it a little bit better, but we're going to be less confident that it's in that range, right? So there's a trade-off of how close you want to be to the true value versus how confident you want to be in the test. Okay. We're going to leave it there today. I know this one's running pretty long. So thanks for sticking around. There's still more to do in this section. I think Yeah, there's more to do in this section. Basically, what if we want to go the other way? What if we're given the confidence interval? How do we work backwards? I'm not 100% sure we'll go through that. Um, Either way, next time we will talk about 8.2, which is basically doing the same thing, except for instead of using the normal distribution, we're going to use a new distribution now called the student's t distribution. So we can't assume everything is normally distributed. So what do we do if it's not? What if it has this other distribution? Okay, so that's what we'll look at next time. Thank you for watching this video today, and I'll see you for the next one.